on Quickly Quantum. A company barely 3 months out of stealth just raised $300 million in a single funding round, betting that fault-tolerant quantum computing needs about 10,000 qubits, not the millions the field has been assuming for years. And the investor list reads like a who's who, from Jeff Bezos to computer scientist Scott Aaronson. Before that, in the headlines, Google says it's taught a quantum computer to fix its own mistakes while it's still running the calculation. IBM just used a quantum chip to model fuel salt inside a fusion reactor for the first time ever. And Quantinuum published a Nature paper arguing quantum computers are finally doing real materials science, not just party tricks. Welcome back to Quickly Quantum, your daily brief on the quantum frontier. It's Friday, July 10, 2026. Let's get into it. Let's start with Google, because this one's a genuine shift in how quantum computers operate, not just another benchmark. Google Quantum AI and DeepMind just published results in Nature showing a quantum computer that learns from its own errors while it's still computing and never has to stop to fix itself. Here's the problem they're solving. Quantum computers spread one reliable, logical qubit, the error-corrected unit you actually compute with, across many physical qubits, so if one glitches, the others catch it. But the calibration, the fine-tuning that keeps those physical qubits behaving, usually happens as a separate step, before or after the real computation, like tuning a guitar between songs instead of while you're playing. What Google did on its Willow superconducting processor is train a reinforcement learning agent, software that improves through trial and reward, the same basic idea behind a lot of game-playing AI, to read the error correction syndromes, the diagnostic signals a quantum computer throws off as it runs, and use them as a live training signal to keep recalibrating on the fly. The result? A 3.5-fold improvement in logical stability against injected drift, meaning when they deliberately destabilize the system, the self-tuning version held together over 3 times better than a static one. As the official Google Quantum AI account put it on X, quote, "We've unified calibration with computation on our Willow processor, training a reinforcement learning agent to stabilize the logical qubit and pave the way towards a quantum computer that continuously learns from its errors." Why should you care if you don't build quantum computers? Because stop and recalibrate is exactly the kind of downtime that makes quantum machines impractical for long, real-world calculations. And taking it off the table is one of those unglamorous engineering wins that quietly moves the whole field closer to usable. Now, from Google's chip learning to fix itself to a genuinely new use case, fusion energy. IBM, Oak Ridge National Laboratory, and the Cleveland Clinic say they've run the first known quantum computation of fusion-relevant materials chemistry. Using IBM's 156-qubit Heron processor, the team computed 9 molecular configurations of FLIBE, a molten salt made of fluorine, lithium, and beryllium that's a leading candidate for extracting tritium, the fuel fusion reactors need, from inside a working reactor. Why does that require a quantum computer at all? Because simulating how atoms and electrons behave in a molecule like this is exactly the kind of problem classical computers handle poorly. The number of possible quantum states explodes combinatorially as you add atoms, which is a fancy way of saying the math gets impossibly big, impossibly fast. As the analyst Equinox26 summarized on X, the calculation modeled fusion-relevant plasma material behavior, a problem classical computers handle poorly because of that combinatorial complexity. The story ties into the U.S. Genesis mission initiative, and it's corroborated by IBM's own newsroom release, not just a press blurb floating around. Now, I want to be clear about scale here. 9 molecular configurations is a research demonstration, not a fusion reactor breakthrough. Nobody's building a power plant off this tomorrow. But it's a real, verifiable first, and chemistry simulation, modeling molecules and materials, is one of the few areas where near-term quantum computers, even before full fault tolerance, are expected to earn their keep. If quantum's going to prove its worth before the big fault-tolerant machines arrive, this is the kind of unglamorous, specific, checkable result that actually counts. Now, sticking with real science over stunts, Quantinuum, working with Caltech, Fermionic, EPFL, and TU Munich, published Nature results out of its H2 trapped ion computer, a 56-qubit system where the qubits are individual charged atoms held in place by electric fields, instead of Google's superconducting circuits. The team simulated Ising model thermalization dynamics, essentially how a simplified magnetic material settles into equilibrium over time, on timescales that challenge classical simulation methods. The framing matters. This is pitched as a shift away from narrow quantum advantage demonstrations, the kind of carefully chosen stunt where a quantum computer beats a classical one at a problem nobody actually needed solved, and toward real material science utility. Worth a beat of context here, because it matters for the main story coming up. Quantinuum just filed to go public at a $12.7 billion valuation, which tells you the trapped ion camp is not short on confidence or capital right now. Between Google's superconducting approach, Quantinuum's trapped ions, and, hold that thought, it's about to matter, a wave of neutral atom startups making very different bets about how few qubits you actually need, this is shaping up to be a real architecture fight, not a one-horse race. Nobody's declared a winner, and honestly, that's good for the field. Real competition between fundamentally different hardware bets is exactly what you want when the stakes are this high. Now, a few more headlines worth your attention before we get to today's big story. QTech, the Dutch research consortium, released a new open architecture superconducting processor called Tuna-17 onto its Quantum Inspire cloud platform. Open architecture meaning outside researchers can actually see and tinker with the chip's design, not just rent time on a black box. It's a modest release, but it's another accessible European hardware option in a field where access to real quantum hardware is still the bottleneck for a lot of academic research. Next, out of the silicon qubit camp, Dirac is reporting that its CMOS-compatible spin qubit array, CMOS being the same manufacturing process that makes your phone's chips, which is the whole selling point of silicon qubits that you could theoretically build them on existing chip factories, is holding 99% fidelity as it scales up to 8 qubits. That's a real data point for the argument that silicon can scale where superconducting and trapped ion approaches struggle, though this comes from Quantum Zeitgeist and we haven't independently confirmed it yet. It's a single source report for now. Also single source, also worth watching. Google is opening a university grant program soliciting academic proposals aimed at 2 specific near-term bottlenecks on the road to fault tolerance. Interesting that Google's funding outside labs even while racing ahead in-house. The error learning story you just heard is proof of that. And finally, out of Hefei National Laboratory in China, researchers say a new calibration workflow they're calling Elia Cafe pushed 2-qubit gate error below 0.007% on an 84-qubit superconducting chip, a real fidelity record for China's quantum hardware program if it holds up. That one's also single source via Quantum Zeitgeist, so file it as a notable claim, not yet independently verified. Now, all of that is the supporting cast. Today's headline act is a funding round that's forcing the entire field to argue about one number. How many qubits does fault tolerance actually need? Our main story today, the 10,000 qubit bet. Oratomic, a quantum computing startup spun out of Caltech and Harvard Research, just closed a $300 million Series A, barely 3 months after coming out of stealth. The Quantum Insider first reported the raise, and it's since been corroborated by SiliconANGLE, FinSMEs, Quantum Zeitgeist, and Yahoo Finance. Let's start with who's actually behind the money, because the list is genuinely unusual for a quantum startup. The round was co-led by Arch Venture Partners, Spark Capital, and Khosla Ventures, with checks from Jeff Bezos' investment vehicle Bezos Expeditions, computer scientist Scott Aronson, Index Ventures, General Catalyst, Lower Carbon Capital, Bain Capital, and a long list of others. This isn't spray and pray venture money. It's a concentrated bet on one specific, falsifiable technical claim. Here's that claim in plain terms. For decades, the working assumption in quantum computing has been that a cryptographically relevant, fault-tolerant machine, one powerful and reliable enough to run Shor's algorithm, the quantum algorithm that can break the public key encryption protecting basically all of today's internet traffic and banking, would need something like 1 million physical qubits. Oratomic's founding research, done with Caltech physicist Manuel Endres, argues that number might actually be somewhere between 10,000 and 26,000 qubits, using neutral atoms, individual atoms trapped and held in place by finely focused laser beams, instead of the superconducting circuits or trapped ions other companies use. Because you can physically move those trapped atoms around mid-computation, the company argues you can run a much more efficient error correction scheme, one co-founder described as cutting the number of physical atoms needed to build one reliable logical qubit from roughly 1,000 down to about 5. That's not a hardware breakthrough yet. It's a theoretical result. But Endres has already demonstrated arrays holding around 6,000 trapped atomic qubits in the lab, giving the company at least an experimental toehold on the scale it's claiming to need. Why does any of this matter if you're not building quantum computers? Because the premise touches your data. A fault-tolerant machine that can run Shor's algorithm is the thing that breaks the encryption protecting your bank account, your medical records, basically anything secured with today's standard public key systems, which is exactly why governments and standards bodies worldwide are already racing to migrate to post-quantum cryptography, with many plans targeting completion by 2035. If Oratomic's math is right, and the qubit count needed is in the tens of thousands rather than the millions, that timeline compresses hard. If it's wrong, nothing changes. And this isn't happening in a vacuum. Private quantum investment more than doubled to about $4.9 billion in 2025, and Oratomic is stepping into a genuinely crowded fault tolerance race. Neutral atom rival Atom Computing has also raised $300 million on a similar architecture. Q-era computing is working the same neutral atom angle with AWS, and the incumbents, Google, IBM, and Quantinuum, which just filed to go public at that $12.7 billion valuation, are all pursuing fault tolerance through superconducting circuits or trapped ions instead. $300 million for a 3-month-old company is either a very smart early bet or a very expensive one. So who's buying this thesis, and who's raising an eyebrow? Let's start with one of the lead investors himself. Vinod Khosla of Khosla Ventures posted on X that his firm, quote, made the largest initial investment yet, as we did in OpenAI, into Oratomic after we looked at a dozen quantum starts in a decade, framing the bet explicitly around getting to, quote, the true symbol of getting to quantum computing first, meaning Shor's algorithm. That's about as direct a comparison to OpenAI's early days as a venture capitalist can make, and it tells you Khosla isn't hedging his enthusiasm, even if the underlying science is still mostly on paper. On X, investor at Investor Denis flagged a detail worth sitting with. Inflection, itself a neutral atom quantum company, was one of the participants in this round, which means a competitor in the same hardware family chose to invest in Oratomic rather than treat it purely as a rival. That's the kind of signal that either means the neutral atom camp genuinely believes this architecture is the one to bet the field's future on, collectively, or it means everyone's quietly hedging by buying a piece of the competition. For the technical case, at Guangyu Robert, an MIT-affiliated founder, walked through why fault tolerance matters so much in the first place and pointed out that CEO Dolev Blufstein is the first author on 4 Nature and Science papers from his PhD work, built on a series of influential papers out of Harvard, Caltech, and MIT. Meant a real pedigree point for the expert listener. This isn't a hardware company slapping a paper onto a press release. It's researchers with a strong publication record betting their own credibility on the math holding up. Analyst at Reed Futurist summed up the mechanism plainly on X. By physically moving atoms during an, quote, ultra-efficient error correction scheme, Oratomic projects it can reach full fault tolerance with just 10 to 20,000 physical qubits. Now here's the part that keeps me from getting fully swept up. This is a bet on math, not hardware. The 10,000 qubit figure comes from a theoretical analysis. Turning that paper into working silicon and laser hardware at scale is a step Oratomic hasn't demonstrated yet. And CEO Dolev Blufstein himself hasn't oversold it. At the company's March launch, he said, quote, it is plausible, although not guaranteed, that we will have a fault-tolerant quantum computer by the end of the decade, which is about as hedged as a founder gets while still cashing a $300 million check. And it's worth remembering, IBM isn't sitting still waiting to find out who's right. The company committed more than $10 billion in June to its own roadmap toward a large-scale fault-tolerant machine, targeting delivery in 2029 on completely different hardware. If Oratomic's math is wrong, IBM's bet doesn't need it to be right. Hype check time. I'm putting this one at a 6 out of 10 on substance. Here's why. The qubit count thesis is grounded in real, credible physics from a team with a strong publication record, and there's an actual experimental data point, 6,000 trapped atoms already demonstrated, behind it. But the leap from, we think 10,000 qubits might be enough, in theory, to fault-tolerant quantum computer by the end of the decade is still a leap, and even the CEO says so out loud. Real science, real money, unproven hardware. That's a 6, not a 3, and not a 9. Watch what happens when Oratomic actually tries to build toward that qubit count in silicon and lasers. That's the number that turns this from a great pitch deck into a real machine. If this episode helped you make sense of the 10,000 qubit bet or Google's self-correcting quantum chip, follow Quickly Quantum wherever you're listening. New episodes land every day, and this field is moving fast enough that skipping a day means missing something real. And if you know someone who'd get a kick out of any of this, send them the show. That's how it grows. That's Quickly Quantum for today. New episodes every day. This is an AI-voiced podcast, created and built by a real person using today's cutting-edge technology. And remember, nothing on this show is financial advice. I'm Brian Lampert. See you tomorrow.